Good day, students. On this clip, we're going to be going over the second example using the formal definition of limits or the epsilon delta proofs to prove that a limit is true. Okay, so let's go ahead and write down the question for example 2. So for example 2, uh, prove that, prove that, let me write that again, prove that the limit as x approaches 3 of the function 4x minus 1 equals 11. So we're going to prove this, okay? So before I go ahead and start the proof, let's just go over the definition of the formal definition of limits again, all right? So just write down the definition. This is what is going to be the guide, our guide for solving this problem, okay? So the definition is um, if we have a and L, a and L in a set of real numbers, okay? A and L in a set of real numbers. Then we say this as the limit. The limit as x approaches this a, this real number of the function f of x equals to L. This basically, this statement, this limit statement means, what it means is that for any epsilon, epsilon represents a number, a real number, for any epsilon greater than 0, there exists another number called delta greater than 0 such that whenever you have a neighborhood x minus a neighborhood around delta, this implies that there is going to be an f of x minus L neighborhood around epsilon. Okay, so if you have if this limit of f of x as x approaches equals L, that means that for any epsilon greater than 0, you're going to have a delta that satisfies this equation. So if you have a delta neighborhood around x, defined by x plus 0, x minus a, you are going to have, this implies automatically that you have an epsilon neighborhood around f of x, which is f of x plus L times f of x minus L. Okay, so that's basically what the definition of a limit is. So this is what we're going to be using to do our proof. All right. So our proof can be broken down into two parts. We're going to do the part 1 first. So for part 1, this part we're going to find, the goal here is to find the appropriate, delta. Okay, find the appropriate delta such that x minus a is less than delta will imply that f of x minus L is less than epsilon. All right. So how do we do this? All we need to do to find the appropriate delta is we need to work backwards. Okay. So what we need to do is we need to work backwards, work backwards, from f of x minus L, the absolute value of f of x minus L. We'll work backwards from here, then we can find the appropriate delta. Okay, we can find the appropriate delta. All right, so I wrote down this plan using the general components of the definition. So let's narrow it down to this problem. Okay, what is f of x? What is a? What is L in this problem? Let's define what they are and then use these actual figures to actually solve the problem. So what we're going to do is we're going to set a. A is going to be what the limit is approaching. X is approaching 3, so for this definition, x is approaching a, we're going to have a equals 3 because that's what x is approaching. All right, and then L is what the function is going to be approaching as x approaches that value. So the limiting function for the limiting value for the function is 11. And what is our function f of x? Our function f of x is going to be 4x minus 1. That's what our function is going to be. So we're going to have 4x minus 1 as our function. Okay, so these are what we're going to be using to do the proof. So the plan was to start from f of x minus L, and then we're going to we're going to work backwards from here to get the appropriate delta. Okay, so the goal in most cases, when you simplify this, you should be able to get a multiple of x minus a. All right, so let's go ahead and find the appropriate delta that can make this work. So we're going to start from f of x. So start with um, f of x minus L, absolute value. And then we know from our definition that this is less than epsilon. We're not going to use this part yet, but we just know that this is true, right? So the function is 4x minus 11. I'm going to put it in here. So I'm going to put 4x minus 1, sorry, minus L. L is 11. Okay, this is less than epsilon. So let's go ahead and simplify the left side and see if we can get an x minus a multiple here so that we can know the appropriate delta to select. So if we simplify this, we're going to have absolute value of 4x minus 12. We know this is less than epsilon, and then we can factor out the 4 from here, and then voila, we have x minus 3. Check this out. Our a is 3, so this is technically, this is like 4 times x minus a. Well, remember, this is what we wanted. This is the left side of the definition of limits, x minus a here. We always want that to come out. So we already have an f of it. We have an x minus a there, which is perfect. So what we're going to do next is we're going to, since this is less than delta, since this is less than epsilon, what we're going to do is we're going to let 4 delta equals epsilon. Okay, so I just took this piece right here and I set it to delta. Okay, so we substitute this for delta. Okay, so if 4 delta equals epsilon, we just simply get delta by itself by dividing both sides by 4, right? So we're gonna have, this implies that delta is equal to epsilon over 4. So this is the appropriate delta that we need to make the proof work. Okay, so appropriate delta that satisfies x minus a less than delta implies f of x minus L is less than epsilon. Okay, so this is the delta that's going to make this work. So now that we have the appropriate delta, we're going to do the proof. Okay, so the proof, what we're going to do in the proof, the goal here is to show that um, show that basically show that if x minus a is less than delta, that implies that f of x minus L is less than epsilon. This is what we're going to show. If we can show this, then we're done. Okay, so show that this implies this for any epsilon greater than 0. All right, so we're going to go ahead and start the proof right now. Okay, all right. All right, so let's do the proof. Just a quick addition, just to ensure that our neighborhood, our delta neighborhood is non-zero, let's just add an additional detail to our definition right here. So just to ensure that we have a non-zero neighborhood, remember delta is greater than 0, we just have to add a 0. This has to be bigger than 0 or else we can have a neighborhood that does not exist, and we don't want that to be the case. So we're going to set the lower limits, 0. Our delta neighborhood has to be bigger than 0. Okay, so we don't have a 0, a non-existent neighborhood. All right, so let's go ahead and do the proof. So we now know that we're going to say, let us have let's say we have a delta neighborhood for some epsilon greater than 0. So let us have 0 is less than x minus a. A in this case is going to be 3. Let x minus 3 be less than delta for some epsilon greater than or equal to 0. Now, can we show that this implies that f of x minus L is less than epsilon? That's the goal. If we can show that, then we're good. All right, so what we're going to do is we're going to start with f of x minus L. And if I can show that this left side is less than epsilon, then I'm in good shape. Okay, so f of x minus L is basically the function, the original function, which is 4x minus 1. This is f of x minus L. L is 11. All right, so let's do some algebra with this. So let's simplify this a little bit. So if I simplify this, what do I get? I get this becomes, let me write my ones well so people don't get, so you don't get confused. So this is 1 and this is 11. This becomes 4x minus 12, absolute value. We can factor out a 4 and we're left with x minus 3. Okay, now what can we say from here? Uh, we said earlier that x minus 3 is less than delta, right? So if I substitute delta for x minus 3, I know for sure that the substitution will result in this inequality being less than what I have, okay? So since x minus 3 is less than delta, this has to be less than 4 delta, right? Because 4 and 4 are the same. If I cover up this 4 and cover up this 4, I'll end up with this original remark that I made here. X minus 3 is less than delta, all right? So this is less than that. But wait a minute. We already have, um, we already selected an epsilon. An epsilon, I mean a delta which is epsilon over 4. So we're going to make that substitution next. So let me just write down the reasons right aside. So this remark we could conclude because we said earlier that x minus 3 is less than delta, right? So then we can assume that because if I times this by 4 and times that by 4, I'll end up with this inequality. So this is true. Now by substitution, I'm going to end up with the remark of, this is going to now become, I'm going to have 4 times x minus 3 is less than 4 times epsilon over 4, right? And then if I reduce that, this is going to be less than, because the 4 and the 4 cancels out, so it's less than epsilon. Okay, so this is less than that, and that's less than epsilon. So I can just bring this down the left side. So I have 4x minus 1 minus 11 is less than epsilon. What does this remark mean? Let me shift it to the right a little bit. What on earth does this remark mean? This remark basically means that uh, f of x minus L is less than epsilon based on our using our original assumption. That is exactly what we wanted to show. So this basically completes the proof. All right. So this remark arriving at f of x minus L is less than e. This completes the proof. Okay. Completes the proof. All right. So and then the reason for this one right here. Let me write down the reason. The reason why we could make this one right here is by substitution. Substitution. Okay. So there you have it. So thanks so much for watching this video. And please uh, do feel free to subscribe to my videos right here. A collection of more videos on mathcodeserve.com. And if you like this video, you can click like. And then feel free to also request videos in the future. If you have any questions, I'll be glad to go over it with you. So thanks again for watching this video and have a wonderful day.